Hey everyone, and welcome back to The Explainer. I'm genuinely thrilled you're tuning in today because we're not just looking at standard, everyday math here. We are unpacking the ultimate fundamental toolkit for literally decoding the entire physical universe. Whether you're trying to measure the width of a single human hair or calculate the distance to a galaxy far, far away, the concepts we're diving into today are exactly what makes science, engineering, and really our entire modern world possible. Okay, let's dive right into this. Have you ever wondered what actually happens when a team of literal rocket scientists makes a simple mathematical typo? Well, there's no sugarcoating it. It's an absolute disaster. In 1998, NASA completely lost the Mars Climate Orbiter. We're talking a multi-million-dollar spacecraft, just gone. Why? Because one engineering team was using English units and the other was using metric. Boom. Or think about Air Canada Flight 143, the famous Gimli glider. It completely ran out of fuel mid-flight. And again, this was due to a lethal confusion between pounds and kilograms during a routine ground calculation. So you see, these aren't just, abstract numbers on a chalkboard. They are literally matters of life and death and incredible financial loss. So this brings us to a rather massive question. Why is it so incredibly important to have a standard system of measurement? Well, the truth is, when we're dealing with science, technology, and engineering, units are absolutely not just optional little labels. They're critical infrastructure. Without a shared, standardized system, our measurements are completely meaningless. And as we just saw, that lack of meaning, it can literally crash spaceships. So we obviously need a bulletproof solution. And here is exactly how we're going to build that solution today. First up, the SI standard. Second, the art of conversion. Third, scaling reality. Fourth, mastering scientific notation. And finally, step 5, integration. Step 1, the SI standard, bringing order to chaos.
Now, before we can calculate anything at all, we have to establish a universal, stable standard for assigning quantities. See, historically, humanity relied on these totally subjective body part measurements, like, the length of a king's foot, which, as you can probably guess, was just pure chaos. To fix this, the global scientific community uses the International System of Units, or the SI system. And what is just absolutely amazing about this system is its sheer elegance. It brings total order to the universe using just 7 foundational base units. We've got seconds for time, meters for length, kilograms for mass, amperes for electric current, Kelvin for temperature, moles for the amount of substance, and candelas for luminous intensity. And from just these 7 pillars plus a handful of prefixes, we can derive literally every other measurement. It truly is the universal language of science.
Moving on to step 2, the art of conversion, dimensional analysis. But of course, just knowing the standard is completely useless to us if we can't safely translate between different measurements, right? We call this translation process dimensional analysis. And honestly, I want you to think about dimensional analysis not just as tedious math, but as a highly satisfying logical puzzle. The rule of the game is super simple. You just carry your units through every single step of your calculation, and you strategically multiply by a conversion factor. Now, a conversion factor is really just a fraction that equals exactly 1. The trick is you make sure to place the unit you don't want in the denominator. Why? So it neatly cancels out. Let's actually look at this in action with a quick example. See, we want to convert 55 kilometers into meters. Well, we know our conversion factor is that 1 kilometer equals 10 to the power of 3, or 1,000 meters. So we just multiply 55 kilometers by that fraction, 1,000 meters over 1 kilometer. And because we place kilometers down there in the denominator, it elegantly cancels out the kilometers in our starting number, leaving us safely with exactly what we want, 55,000 meters. Now, what's really fascinating is how we can apply this to a real-world conflict. Picture this. You're driving on the expressway at 35 kilometers per hour, but you look up and the speed limit is posted as 17 meters per second. So, are you speeding? Well, you can't just compare kilometers per hour directly to meters per second. That's totally comparing apples to oranges. We have to run a multi-step algebraic translation to reveal the actual truth. So let's pull out our toolkit and guide ourselves through the sequential logic here. Step 1, we actually need 2 conversion factors this time because we have to change both distance and time. We need to go from kilometers to meters and from hours to seconds. Step 2, we multiply our starting speed, 35 kilometers per hour, by 1,000 meters over 1 kilometer. That cancels the kilometers. Then we multiply that whole thing by 1 hour over 3,600 seconds, which neatly cancels out the hours. Do the math, and it gives us 9.72 meters per second. Finally, step 3, we compare.
At 9.72 meters per second, our driver is safely, comfortably below that 17 meters per second limit. Our toolkit just solved the mystery.
Which brings us to step 3, scaling reality, the vast and the microscopic. So, having successfully navigated unit conversion, we now have to face another wild reality of the physical universe. The universe definitely doesn't operate on a single human-sized scale. Just think about the sheer contrast for a second. On one hand, we are living in a vastly expansive cosmos where the distances between planets and giant cosmic nebulas are just mind-bogglingly huge. But on the exact opposite hand, reality is also made up of objects like tiny bacteria and individual atoms that are so incredibly microscopic they're completely invisible to the naked eye. If we actually tried to write down these measurements using standard numbers, we would literally drown in a sea of zeros. Standard numbers just completely fail us at these extremes. Let's fix that in step 4, master scientific notation. To solve this massive problem of writing way too many zeros, physicists developed what I consider the ultimate shorthand tool. The absolutely crucial point here is understanding standard form. Basically, every single number, no matter how gigantically large or infinitesimally small, can be expressed as a base number, let's call it n, multiplied by 10 to the power of a. The rules for this are incredibly strict, but they're also super simple. First, n absolutely must be a number between 1 and 10. It can be an integer or it can be a decimal, but it has to fall in that range. And a, our exponent, that's just an integer, and it can be either positive or negative. Let's clearly lay out the actual mechanical rules for making this happen. Rule number 1, n should include only one non-zero digit to the left at the decimal point. That's how we guarantee it stays between 1 and 10. Rule number 2, the exponent a simply reflects exactly how many times you moved that decimal point to get there. If you have to move the decimal point to the left to shrink down a massive number, your exponent is going to be positive. But if you move the decimal point to the right to enlarge a tiny, tiny decimal, then your exponent becomes negative. Let's demonstrate this by actually applying the rules to a really, really large number. The temperature at the absolute core of the sun is 15,700,000 Kelvin. Now, to get our n to sit nicely between 1 and 10, we have to take the invisible decimal point that's hiding all the way at the far right of that number, and we span it 7 digits to the left until it sits right between the 1 and the 5. And because we move left 7 spaces, our exponent becomes a positive 7. That gives us a beautifully neat, super clean 1.57 times 10 to the power of 7 Kelvin. Now let's contrast the blistering sun with the ridiculously microscopic radius of a single hydrogen atom. Think about a number with 10 zeros after the decimal point before you even hit a solid digit. Try to mentally move that decimal point to the right with me. To get a number between 1 and 10, we have to drag that little dot all the way past those 10 zeros and land it right after the 2. That gives us 2.5. And since we moved it 11 spaces to the right, our exponent is negative 11, giving us 2.5 times 10 to the negative 11. I mean, it's just such an elegant, powerful system for handling the extremes of reality. And finally, step 5, integration, putting it all together. Now that we've got our individual tools mastered, it is time to actually bring them all together. Because in real-world physics problems, units, conversions, and scientific notation, they don't just live in isolation. They have to work together harmoniously. So, if you're going to calculate anything in physics, you absolutely need these final survival rules for doing arithmetic with scientific notation. Here they are. If you want to add or subtract two numbers, you must align their exponents first. You have to be dealing with the exact same scale before you do the math. Now, if you're multiplying, you simply add the exponents together. Easy. And if you're dividing, you guessed it, you subtract the exponents. This is absolutely crucial because it ensures that those massive scale differences are properly managed during complex calculations. And honestly, this brilliantly illustrates our entire high-stakes toolkit. Think about what we've built today. We've established universal SI standards, so we are literally all speaking the exact same scientific language. We've mastered dimensional analysis to safely cancel unwanted units and navigate tricky conversions without crashing a spaceship, mind you. And we've unlocked scientific notation to elegantly handle the massive scale of the universe. And we learned how to integrate those complex calculations with ease by aligning and managing our exponents. As we wrap up this explainer today, I really want to leave you with a bit of a provocative thought. The very next time you measure something, whether that's the speed of your car, the distance of your morning run, or just checking the temperature outside, I want you to think about the invisible infrastructure beneath that number. When you measure the world around you today, how will you ensure your numbers accurately reflect reality? Because remember, a number is really just a symbol, but these tools, standards, units, and notation, they are the absolutely crucial link that stands between properly understanding our brilliant universe and accidentally crashing a satellite on Mars. Thanks so much for joining me on The Explainer today. Keep learning, and I will catch you next time.